Hello there, and welcome to the Dreamy Ocean Channel. As you settle into your space, perhaps allow your shoulders to soften. Let the tension gently release from your brow and simply breathe. Have you ever wondered what ancient, unseen voices might whisper from the deepest, darkest trenches of our own planet where sunlight never reaches and the pressure is unimaginable? Tonight, we journey to these extreme depths to explore the enigma of undecipherable signals emanating from places where life as we know it should not exist. A world of profound silence, yet one that seems to hum with a presence we cannot yet comprehend, sending out transmissions into the crushing darkness. These are the whispers of an alien world hidden just beneath the surface of our own. Let your mind drift now, carried by the subtle currents of curiosity, as we descend into these profound secrets of the ocean floor. The whispers from the sunken world. The journey into the ocean's profound depths begins not with a sudden plunge, but a gradual, almost imperceptible descent, a slow relinquishing of the sunlit world. From the shimmering, vibrant surface where the warmth of solar rays penetrates and the currents ripple with life, we begin to sink gently, passing through the epipelagic zone, a sun-drenched realm teeming with familiar creatures. As we drift further, the light begins its slow, agonizing fade, transforming from a brilliant azure to a muted indigo, then to a deep, bruised violet, signaling our entry into the mesopelagic or twilight zone. Here, the last vestiges of daylight struggle to pierce the immense liquid ceiling above, painting the environment in ethereal, shifting hues of gloom. A place where many creatures migrate upwards in the protective cloak of night, only to retreat into the deeper shadows as dawn approaches. With each passing moment, the water around us grows colder, the pressure mounts, and the world outside becomes a vast, crushing embrace. We leave behind the twilight, crossing an invisible threshold into the bathypelagic zone, a realm of perpetual night where the sun's light has entirely vanished, never to penetrate. Here, the only illumination comes from the ephemeral flashes of bioluminescence, the living light emitted by the inhabitants themselves, glowing softly in the abyssal blackness, like scattered jewels in an infinite, ink-dark cavern. This is a universe unto itself, detached from the rhythms of day and night that govern the surface, a place where time seems to slow, stretched thin by the immense forces at play. The water, now nearing freezing temperatures, presses in from every direction, a colossal weight that would instantly crush any unprotected vessel. Yet it is the natural home for a myriad of specialized forms of life adapted to this crushing environment. Even deeper beyond the bathypelagic lies the abyssal pelagic zone, stretching across the vast flat plains of the ocean floor, a landscape sculpted by unimaginable pressures and the slow, relentless accumulation of sediment over eons. This is the true abyss, a seemingly featureless expanse that covers over half of our planet's surface, yet remains more unexplored than the surface of Mars. Here, the pressure can exceed 700 times that experienced at sea level, equivalent to the weight of a large elephant standing on a postage stamp. The temperature hovers just a few degrees above freezing, a constant chilling embrace that permeates every corner of this colossal underwater desert. It is a world of stark contrasts, crushing force yet delicate life, absolute darkness yet occasional vibrant bursts of living light. And then there are the deepest scars on our planet's face, the hadal-pelagic zone found within the ocean's trenches, plunging down to 11,000 meters, nearly 7 miles beneath the waves. These narrow, crescent-shaped chasms, such as the Mariana Trench, represent the ultimate frontiers of earthly existence, pushing the boundaries of what life can endure. Here, the pressure reaches an astonishing 1,100 times atmospheric pressure, a force so immense that it can literally change the chemical properties of water, making it denser, more viscous. Within these trenches, the geological processes of plate tectonics grind slowly onward, shaping the very crust of our world. And in doing so, they create a unique environment, a crucible, where the most extreme forms of life cling to existence, surviving. In conditions that beggar belief, feeding on sparse organic matter that drifts down from above, or on the chemical energy released from hydrothermal vents. In this profound darkness, the properties of the medium itself become paramount. Water, that ubiquitous substance, behaves very differently at these depths. While light, in the form of electromagnetic waves, is almost entirely absorbed within the first few hundred meters, rendering the abyss perpetually dark, sound waves tell a different story. Water is an incredibly efficient conductor of sound, far more so than air. Vibrations can travel through this dense liquid medium for thousands of miles, carrying information and energy across vast ocean basins. The speed of sound in seawater is approximately 1,500 meters per second, nearly 5 times faster than in air, and it varies subtly with temperature, pressure, and salinity. These variations create complex acoustic channels, guiding sound waves along specific paths, allowing them to propagate with remarkable clarity and range over immense distances. It is this characteristic of water that transforms the deep ocean from a silent void into a potential canvas for whispers. Even in the absence of light, sound can paint a detailed, if abstract, picture of the environment. The natural sounds of the deep are myriad: the gentle sifting of sediment, the slow grinding movement of tectonic plates, the distant rumble of underwater earthquakes, the explosive release of superheated fluids from hydrothermal vents, creating a chorus of geological activity. These vents, often found along mid-ocean ridges, spew forth mineral-rich water at temperatures that can exceed 400 degrees Celsius, forming towering chimney-like structures where chemosynthetic ecosystems flourish, entirely independent of sunlight. The constant outflow from these vents, along with the associated seismic activity, generates a unique acoustic signature, a deep, resonant hum that permeates localized areas of the ocean floor, a natural voice of the planet itself. Beyond these geological utterances, there are the low-frequency calls of large marine mammals, particularly the great whales, whose intricate vocalizations are designed to travel across entire ocean basins, communicating with one another over distances of hundreds, even thousands of kilometers. Their haunting songs, often produced in the infrasonic range below the threshold of human hearing, are a testament to the ocean's acoustic efficiency. These biological signals, along with the clicks and chirps of other deep-sea creatures, form a complex, ever-shifting soundscape, a living orchestra of the deep, each species adding its unique melody or rhythm to the vast underwater composition. Even the faint scraping of a crustacean on a rock, amplified by the sensitive hydrophones deployed by scientists, can become a distinct event in this otherwise muted world. Yet even with this understanding of natural phenomena, the deep ocean holds secrets that continue to baffle our scientific instruments. For decades, researchers have deployed sensitive hydrophones and other detection equipment into these abyssal zones, listening intently to the planet's pulse. While many sounds can be attributed to known geological or biological sources, there have been recurring instances of anomalous signals, strange acoustic patterns, and even faint, puzzling electromagnetic disturbances that defy conventional explanation. These are not the familiar rumbles of earthquakes, nor the mournful calls of whales, nor the crackle of hydrothermal vents. Instead, they are often described as unusual, persistent, and sometimes rhythmic transmissions, emanating from regions of the ocean floor where our current understanding suggests such activity should not occur. These unexplained whispers from the sunken world are not mere fleeting anomalies. Some have been detected repeatedly, sometimes for extended durations across vast stretches of the ocean floor. They are not easily dismissed as equipment malfunctions or random noise. Their persistence, their unique characteristics, and their origins in regions of extreme pressure and darkness have led scientists to meticulously re-evaluate every known natural process, every conceivable source of sound or electromagnetic energy that could possibly exist in such an environment. The very notion of electromagnetic signals penetrating and propagating through miles of dense, conductive seawater presents a profound challenge to our understanding of physics, as salt water is known to rapidly attenuate radio waves, effectively blocking them over short distances. The deeper we delve into the ocean's profound silence, the more profound the questions become. What could generate such signals in a realm so devoid of light, so crushing in its embrace, so distant from the influences of the surface world? Are these echoes of undiscovered geological processes, perhaps entirely new forms of tectonic activity, or exotic chemical reactions occurring deep within the Earth's crust that transmit energy in ways we have yet to comprehend? Or do they hint at something far more extraordinary, something biological, perhaps even intelligent, that has evolved to thrive and communicate in ways utterly alien to our surface-dwelling perspectives? The very act of listening in the dark, of straining to discern pattern from noise, pushes the boundaries of human curiosity and technological ingenuity, compelling us to consider possibilities that extend far beyond our current scientific paradigms. As we continue this gentle descent, allowing the sheer scale and mystery of the deep ocean to envelop our thoughts, we acknowledge that this sunken world, with its crushing pressures and eternal night, is far from truly silent. It is a place that hums with its own deep, resonant life, a place where the planet itself breathes and shifts, and where perhaps entirely unknown voices are waiting to be understood. The quest to decipher these whispers from the abyss is a journey into the very heart of the unknown, a patient act of listening in the profound darkness, hoping to catch a glimpse of the secrets held within Earth's deepest, most enigmatic frontier. The stage is set, the deep ocean awaits, and its mysterious transmissions continue to beckon us into an exploration of the truly extraordinary, gently guiding our minds into the vast, slumbering depths, a realm of pressure and cold. As we continue our gentle, almost imperceptible descent through the water column, the subtle nuances of the abyssal realm begin to assert their profound dominance, shaping every molecule, every current, every whisper of existence within this sunken world. The most immediate and overwhelming sensation, were one able to perceive it, would be the immense, unyielding pressure. This is not merely a force. It is an omnipresent, all-encompassing embrace, an invisible hand pressing in from every conceivable direction, saturating the very fabric of space. For every 10 meters we sink deeper into the ocean, the pressure increases by approximately 1 atmosphere. To put this into perspective, imagine the air that surrounds us at sea level, the weight of the entire column of atmosphere above us, gently resting on our shoulders. Now, multiply that weight by hundreds or even thousands of times. In the abyssal plains at depths of 4,000 meters, and beyond, this hydrostatic pressure can easily exceed 400 atmospheres. This means that every square centimeter of surface area is subjected to a force equivalent to 400 kilograms. To visualize this, consider a large elephant, perhaps weighing 4 metric tons, delicately balanced upon a single postage stamp. Now, imagine not just one such elephant, but hundreds of them stacked invisibly upon every tiny patch of surface, pressing down with relentless, unwavering force. Yet this pressure does not crush in the violent, explosive manner one might envision from science fiction. Instead, it is a slow, pervasive squeeze, a deep compression that works on a molecular level, altering the very properties of matter. Gases, for instance, are compressed into minute volumes, rendering gas-filled organs like the swim bladders, common in shallower fish, utterly useless and dangerous in the deep. Even the water itself becomes subtly denser, its molecules packed more tightly together, transforming it into a medium of extraordinary viscosity under such immense loads. This profound pressure dictates the very architecture of life that can survive here. Creatures of the abyss often possess bodies that are largely fluid-filled, lacking rigid structures or gas pockets that would otherwise collapse. Their tissues are often gelatinous, allowing the internal and external pressures to equalize effectively, making them immune to the crushing force. Their cellular membranes and proteins have evolved unique structures fortified by specialized molecules like trimethylamine, N-oxide, or TMAO, which stabilizes them against the pressure-induced denaturation that would render most surface-dwelling enzymes inert. It is a biological marvel, a testament to evolution's ingenuity, that life can not only endure, but thrive under conditions that would instantly obliterate anything not specifically designed for such an extreme environment. The pressure here is not an obstacle to be overcome, but an intrinsic component of existence, woven into the very fabric of life. Hand in hand with the crushing pressure comes the pervasive, bone-deep cold. As we descend past the thermocline, that invisible boundary layer where warm surface waters rapidly give way to colder, denser depths, the temperature plummets. In the vast reaches of the abyssal zone, the water temperature hovers consistently between a frigid 0 and 4 degrees Celsius, just a few degrees above freezing. This is not the transient cold of a winter's day, but an eternal, unyielding chill, a constant embrace that permeates every corner of this colossal liquid cavern. This profound cold originates from the polar regions, where surface waters chilled to freezing temperatures become incredibly dense and sink, forming vast, slow-moving currents that creep along the ocean floor, circulating through every ocean basin over millennia. This global conveyor belt, known as the thermohaline circulation, acts as the deep ocean's refrigeration system, constantly replenishing the abyssal waters with icy flows. The implications of this pervasive cold are far-reaching. Chemical reactions, the very engine of life, slow dramatically at low temperatures. Metabolic rates in abyssal organisms are profoundly reduced, leading to slower growth, extended lifespans, and a general languidness in movement compared to their surface counterparts. Energy conservation becomes paramount in an environment where resources are scarce, and the cost of maintaining body temperature is irrelevant given the surrounding chill. Enzymes, the biological catalysts that drive cellular processes, must be specially adapted to function efficiently in these frigid conditions, remaining flexible and active where most enzymes would stiffen and cease to operate. This icy embrace shapes not just the physiology of life, but also the physical properties of the water itself, subtly increasing its viscosity and density, creating a medium that feels thicker, more resistant to movement, like moving through a very thin, perfectly clear gel. And then there is the absolute profound absence of light. After the first 200 meters, where the last vestiges of red light are absorbed, followed by green and blue, the sun's radiant energy is completely extinguished. Beyond 1,000 meters, the abyss is plunged into eternal night, a darkness so complete that it defies our terrestrial understanding. This is not merely the absence of light, it is the absence of any solar influence severing the deep ocean from the primary energy source that drives nearly all life on Earth. Photosynthesis, the process by which plants convert sunlight into energy, is utterly impossible here. The vibrant, sun-drenched ecosystems of the surface with their intricate food webs, built upon photosynthetic primary producers, are a distant, forgotten memory. Instead, the abyssal realm relies on an entirely different energy economy. Life here is sustained by the slow, continuous snowfall of organic detritus, from above a gentle rain of decaying organisms, fecal pellets, and discarded exoskeletons known as marine snow. This delicate, shimmering precipitation drifts down through miles of water carrying precious nutrients to the hungry mouths below. In some remarkable areas, life flourishes around hydrothermal vents and cold seeps, where chemosynthetic bacteria harness chemical energy from geological processes forming the base of vibrant, independent ecosystems that exist entirely without sunlight. These localized oases of life are exceptions to the general rule of scarcity islands of abundance in a vast, desolate sea. The combined forces of immense pressure, pervasive cold, and absolute darkness create an environment of extraordinary stillness and stability. Currents, while present, are often far slower and less turbulent than those at the surface, allowing fine sediments to accumulate over geological timescales, forming vast, featureless plains. The absence of light means no daily or seasonal cycles, no photosynthesis-driven migrations, no visual predators relying on sight. It is a world governed by chemical gradients, by touch, by vibration, and by sound, where every sensory input is finely tuned to the unique challenges and opportunities of the abyss. In this realm of such fundamental extremes, where the very conditions of existence push against the boundaries of what we understand, the concept of a signal takes on an even more profound significance. For something to generate a consistent, detectable pattern of energy, be it acoustic or electromagnetic, within this crushing, freezing, lightless environment, requires a source of immense power, or a mechanism of transmission that is incredibly efficient and resilient. The whispers from the sunken world, then, are not just sounds. They are anomalies against a backdrop of absolute physical constraint, a testament to an unknown force operating within a dominion where the rules of the surface world are utterly rewritten. This profound stillness, this deep embrace of pressure and cold, serves only to amplify the mystery of any voice that dares to speak within its depths, drawing us further into the secrets held by the very waters themselves. Sound and electromagnetic waves beneath the surface. Within the crushing embrace of the deep ocean, where pressure reigns supreme and cold permeates every molecule, the very fabric of communication is profoundly altered, shifting from the light-dependent world we know to one dominated by unseen vibrations and subtle, energetic pulses. Sound in particular becomes the primary messenger, a pervasive force that shapes the acoustic landscape of the abyss, allowing whispers to travel across vast, unimaginable distances where light cannot penetrate even a single meter. Unlike the air above which is a relatively sparse medium, water is a dense, incompressible fluid, an almost perfect conductor of sound. Imagine pressing your ear against a solid wall and hearing the subtle vibrations from another room. Water amplifies this effect exponentially, transforming the ocean into a colossal, resonant chamber where every tremor, every faint click, every distant rumble can propagate with astonishing efficiency. The speed at which sound travels through seawater is a crucial factor in its dominance. At approximately 1,500 meters per second, it moves nearly 5 times faster than through the air. We breathe a phenomenon shaped by the interplay of temperature, pressure, and salinity. As we descend, the temperature generally decreases, which would tend to slow sound, but simultaneously, the pressure increases, which tends to speed it up. Salinity. The concentration of dissolved salts also plays a subtle role, increasing sound speed slightly. These competing influences create complex profiles within the water column, leading to fascinating acoustic phenomena. For instance, in many ocean regions, a unique layer exists at depths typically between 800 and 1,200 meters, known as the SOFAR channel, or the sound fixing and ranging channel. Here, the speed of sound reaches a minimum, creating a natural waveguide. Sound waves that enter this channel, whether originating from a geological event or a biological source, tend to refract and bend back towards the channel's axis, becoming trapped within it. This remarkable phenomenon allows low-frequency sounds to travel thousands of miles across entire ocean basins with minimal loss of energy, transforming the deep ocean into a planetary-scale listening post where the faintest distant hum can be carried across continents, a testament to the ocean's profound acoustic properties. The efficiency of sound propagation in water means that the deep ocean is far from silent. It is a world alive with a symphony of natural acoustic events, a constant low-frequency hum that often lies below the threshold of human hearing, yet is profoundly meaningful to the creatures that inhabit these depths. There are the deep, resonant rumbles of distant earthquakes, their seismic energy transmitted through the ocean floor and into the water column, traveling for hundreds of miles as a slow, powerful thrum. Hydrothermal vents, those scorching oases of chemosynthetic life, produce a constant sizzling hiss as superheated water laden with minerals erupts from the Earth's crust, creating a localized, effervescent soundscape. The slow, grinding movement of tectonic plates along underwater fault lines generates a deep, groaning sound, a geological whisper of our planet's relentless internal processes. Even the subtle sifting of sediment, the gentle cascade of marine snow onto the abyssal plain, contributes to this intricate acoustic tapestry, creating a constant soft patter that echoes through the stillness, a slow-motion rain of nutrients. Biologically, the deep ocean also possesses its own vibrant chorus. The colossal baleen whales, magnificent titans of the deep, produce some of the most powerful and far-reaching sounds on Earth. Their haunting, complex vocalizations, often in the infrasonic range, are specifically designed to exploit the SOFAR channel, allowing them to communicate with one another across vast ocean expanses, navigating finding mates, and coordinating their movements over hundreds, even thousands of kilometers. These are not mere calls. They are intricate rhythmic songs carrying information and intent through the dense liquid medium. Other deep-sea creatures, from snapping shrimp to various species of fish, also contribute to this living soundscape, with clicks, chirps, and unique acoustic signatures, each adding its own distinct voice to the collective conversation of the abyss, a testament to sound's vital role in a world without light. However, when we turn our attention to electromagnetic waves such as light or radio signals, the story changes dramatically, becoming one of profound attenuation and rapid dissipation. While sound finds a welcoming, efficient medium in water, electromagnetic waves encounter an almost impenetrable barrier. The very same properties that make seawater an excellent conductor of sound, its density and salinity, render it a formidable obstacle to the propagation of electromagnetic energy. Water, particularly salt water, contains a high concentration of free ions, such as sodium and chloride. These charged particles readily interact with the oscillating electric and magnetic fields of an electromagnetic wave, absorbing its energy and converting it into heat. This process, known as absorption and scattering, rapidly attenuates the wave, causing its strength to diminish exponentially with distance. Consider visible light, the most familiar form of electromagnetic radiation. Even in the clearest ocean waters, red light is almost entirely absorbed within the first few meters, followed by orange, yellow, and green. Blue light, with its shorter wavelength, penetrates the deepest, but even it is completely extinguished by around 1,000 meters, plunging the abyss into perpetual darkness. This profound absorption explains why deep-sea creatures have often evolved without functional eyes, or possess eyes specifically adapted to detect the faint, scattered blue light, or the bioluminescent flashes of other organisms. For radio waves, which have much longer wavelengths than visible light, the challenge is even greater. The conductive nature of seawater acts like a short circuit, effectively eating the electromagnetic energy. The higher the frequency of the radio wave, the more rapidly it is absorbed and dissipated, meaning that conventional radio signals like those used for broadcasting or Wi-Fi cannot penetrate more than a few centimeters or perhaps a meter into the ocean before becoming utterly undetectable. This rapid attenuation is quantified by a concept known as skin depth, which describes the depth at which the intensity of an electromagnetic wave falls to approximately 37% of its surface value. For typical radio frequencies, the skin depth in seawater is incredibly small, often measured in mere centimeters. This physical reality poses an immense challenge for any form of long-range wireless communication or detection beneath the waves. Submarines, for instance, cannot use standard radio to communicate when submerged at any significant depth. They must either surface and deploy an antenna or use specialized extremely low-frequency ELF or very low-frequency VLF radio waves. ELF waves, with frequencies typically ranging from 3 to 300 Hz, and VLF waves from 3 to 30 kHz, represent the only forms of electromagnetic radiation capable of penetrating seawater to any appreciable depth. Their extremely long wavelengths and low frequencies allow them to interact less aggressively with the free ions in the water, reducing absorption. However, even these specialized signals come with severe limitations. To generate ELF waves, colossal antennas, often many miles long, are required, consuming immense amounts of power. The data transmission rate is incredibly slow, often just a few characters per minute, making them suitable only for sending very basic, pre-arranged commands or emergency messages to submerged vessels, rather than complex information. VLF waves offer slightly better data rates and require smaller antennas, but their penetration depth is still limited to a few tens of meters, or at most a few hundred meters, depending on the specific frequency and water conditions. Beyond these shallow depths, even ELF and VLF signals become too weak to be reliably detected. Given this fundamental understanding of physics, that the deep saline ocean is a near-perfect insulator against electromagnetic waves, especially those in the radio frequency spectrum. The reports of unexplained electromagnetic signals emanating from the abyssal floor present an extraordinary scientific puzzle. If these signals are indeed electromagnetic and are truly originating from extreme depths, their existence challenges our current models of wave propagation in conductive media, or points to an entirely unknown mechanism of generation and transmission. What kind of power source, what kind of emitter could possibly overcome the immense attenuating properties of miles of seawater to send a detectable electromagnetic whisper to the surface? The sheer improbability of such a phenomenon based on established physics is precisely what fuels the profound mystery surrounding these enigmatic echoes from the deep, urging us to listen more closely and to question the boundaries of our current understanding. The ocean in its vastness may yet hold secrets that transcend our most fundamental scientific assumptions, beckoning us to contemplate possibilities that stretch beyond the known. Geological rumbles and anthropogenic traces. Even in the profound stillness of the abyssal realm, a deep, pervasive hum often permeates the vast liquid expanse. A symphony composed not of biological melodies alone, but also of the powerful, relentless forces of our planet and the distant, echoing activities of humankind. These are the known voices of the ocean floor, the geological rumbles and the faint anthropogenic traces that provide a crucial backdrop against which the truly mysterious signals will later emerge, offering a baseline of understanding before we delve into the truly anomalous. Among the most fundamental and far-reaching sounds in the deep ocean are those born from the Earth's own restless interior, the seismic symphony of geological rumbles. Beneath the colossal weight of the water column, the planet's tectonic plates are in constant slow-motion conflict, grinding past each other, pulling apart or colliding with unimaginable force. When these immense stresses overcome the friction holding the plates in place, the Earth shudders, releasing vast quantities of energy in the form of an earthquake. Submarine earthquakes occurring beneath the ocean floor generate powerful seismic waves that travel through the solid crust, but also efficiently transfer their energy into the overlying water column, propagating as acoustic waves. These are typically low-frequency deep rumbles, often below the threshold of human hearing, yet detectable by sensitive hydrophones deployed across thousands of miles. The sound can be described as a prolonged guttural growl, a deep, resonant thrum that resonates through the entire ocean basin, carrying the signature of the Earth's internal movements across vast distances, a slow, powerful pulse from the planet's very heart. The duration and intensity of these seismic whispers vary immensely, from the sudden sharp crack of a minor fault slip to the sustained profound roar of a major subduction zone event, which can last for many minutes, even hours, as the Earth slowly settles back into a temporary equilibrium. Closely related to these tectonic movements is the vibrant, often violent activity of underwater volcanoes. Along the mid-ocean ridges where new oceanic crust is continuously formed as plates pull apart, molten rock or magma rises from the Earth's mantle. This process can be effusive, with gentle flows of lava slowly oozing out onto the seafloor, or explosive, erupting with tremendous force. Volcanic eruptions beneath the waves create a distinctive acoustic signature, a chaotic medley of deep rumbles as magma moves through conduits, sharp cracks as new rock fractures under pressure, and a persistent, turbulent hiss as superheated gases and fluids are violently expelled into the cold seawater. Imagine a colossal subterranean forge constantly at work, its immense bellows and hammers echoing through the dense liquid, a continuous murmur of creation and destruction. The sounds can be surprisingly diverse, ranging from the low infrasonic moans of deep magma chambers to the higher frequency pops and crackles of cooling lava rapidly solidifying against the frigid ocean water. These volcanic voices are often localized but can be intense, creating a vibrant, dynamic soundscape in their immediate vicinity, a testament to the planet's raw, untamed power. Perhaps the most iconic geological sound from the deep are the complex acoustic emanations from hydrothermal vents. These extraordinary ecosystems, often found along mid-ocean ridges or in volcanically active areas, are like boiling cauldrons on the seafloor. Seawater seeps into cracks in the crust, becomes superheated by magma, and then erupts back into the ocean through chimney-like structures known as black smokers or white smokers, laden with dissolved minerals. The acoustic signature of these vents is a persistent, effervescent hiss and crackle, a sound like 1,000 tiny champagne bubbles, constantly bursting mixed with the deeper gurgle of turbulent fluid flow. This ceaseless sound is a direct result of the extreme temperature gradient and the chemical reactions occurring as superheated mineral-rich water mixes with the frigid ambient seawater, causing minerals to precipitate and form the towering chimneys. Each vent field, with its unique chemistry and flow rates, contributes a distinctive acoustic texture, a continuous low-level chatter that defines these oases of chemosynthetic life, a constant whisper of geological transformation. Beyond these dynamic geological processes, less frequent but equally powerful events contribute to the deep ocean's known acoustic profile. Submarine landslides, for instance, can generate colossal low-frequency rumblings. When vast quantities of sediment destabilize by earthquakes, steep slopes or powerful currents suddenly give way. They cascade down the continental slopes and onto the abyssal plains. The sheer mass of moving material displacing immense volumes of water creates a thunderous, prolonged roar, a deep, grinding sound that can travel for hundreds of miles, a slow-motion avalanche of mud and rock, echoing through the dark. These events are often powerful enough to generate localized turbidity currents, dense, fast-moving flows of sediment-laden water that can scour the seafloor and leave lasting geological imprints, their passage marked by a sustained, turbulent acoustic signature. Contrasting sharply with these primal geological voices are the anthropogenic traces, the sounds and subtle energetic emanations introduced into the deep ocean by human activity. Even in the most remote abyssal trenches, our presence can be detected often as a distant, persistent drone. Shipping noise is perhaps the most pervasive human-made sound in the ocean. The constant thrumming of ship engines, the cavitation noise generated by rapidly rotating propellers, and the general hydrodynamic noise of vessels moving through water create a low-frequency, continuous background hum that permeates vast stretches of the ocean, especially along major shipping lanes. This ubiquitous sound, a distant mechanical groan, has demonstrably increased over the past century, fundamentally altering the natural soundscape, and in some areas masking the natural biological and geological sounds that marine life relies upon. While primarily an acoustic phenomenon, large vessels can also generate localized weak electromagnetic fields due to their electrical systems, though these fields attenuate very rapidly in seawater and are not typically considered long-range signals. Another significant human contribution to the deep ocean's soundscape comes from active sonar systems. Military navies use powerful directional sonar pings to detect submarines and map the seafloor, emitting sharp, intense pulses of sound that can travel for many miles. Scientific research vessels also employ various forms of sonar, from multi-beam echo sounders for detailed seafloor mapping to sub-bottom profilers for studying sediment layers, all contributing their characteristic series of rapid, percussive pings or longer sweeping chirps to the acoustic environment. These are deliberately engineered sounds designed to probe the depths, and their distinct patterns are easily identifiable by hydrophone arrays. Perhaps the loudest and most impactful anthropogenic sounds are those generated by seismic surveys. Used primarily by the oil and gas industry for exploring hydrocarbon reservoirs beneath the seafloor, and by geophysicists for studying Earth's crustal structure, these surveys involve towing arrays of powerful airguns behind vessels. These airguns release bursts of highly compressed air, creating immensely loud, low-frequency acoustic pulses that penetrate deep into the seafloor. The echoes that return provide detailed images of subsurface geological formations. The sound from a single air gun array can be so intense that it can propagate across entire ocean basins, creating a powerful repetitive thud that, while providing invaluable scientific data, is also a significant source of acoustic disturbance for marine life, especially in its immediate vicinity. Other human activities, though less widespread, also leave their acoustic signatures. Underwater construction, such as the laying of pipelines or the installation of deep-sea observatories, can generate a variety of sounds, from drilling hammering and the operation of remotely operated vehicles. Submarine communication cables, while primarily transmitting optical signals, may emit faint localized electromagnetic fields from their power repeaters, though these are not designed for long-range communication and are rapidly absorbed by the surrounding water. Even the occasional detonation of explosives, whether for military exercises, demolition, or scientific experiments, contributes sharp, intense broadband acoustic energy to the deep. Understanding these known voices, the deep, resonant groans of the earth, the effervescent hiss of hydrothermal vents, the distant thrum of ships, and the sharp pings of sonar, is crucial. They represent the established baseline, the expected sounds within the profound darkness. When our instruments detect something that does not fit these categories, something that defies the known physics of sound and electromagnetic propagation in seawater, the mystery deepens, compelling us to consider sources and mechanisms that lie beyond our current understanding, drawing us further into the true enigma of the ocean's whispers, signals beyond current understanding. Having gently traversed the landscape of known sounds, the deep, resonant groans of the Earth's restless crust, the effervescent hiss of hydrothermal vents, and the distant mechanical thrum of human endeavor, we now drift into a realm of even deeper enigma. Here, our sensitive instruments, meticulously placed within the crushing, cold embrace of the abyss, occasionally register something profoundly different, something that defies the established categories, a subtle, persistent presence that whispers from the profound darkness. These are the undecipherable hums, the anomalous signals that have for decades puzzled the most astute minds in oceanography and geophysics, pushing the boundaries of what we understand about our own planet's hidden depths. These enigmatic acoustic signals are not mere fleeting noises. They are often characterized by their persistence, their unique spectral signatures, and most compellingly, their origins in regions where no known geological or biological source should exist. Imagine listening to a vast, silent room, and suddenly, a faint rhythmic pulse begins to resonate, a low-frequency throb that possesses an almost deliberate quality, yet originates from a point where all conventional expectations are utterly confounded. One such famous example, recorded repeatedly by the US National Oceanic and Atmospheric Administration, or NOAA hydrophones, in the late 1990s, was affectionately, or perhaps apprehensively, termed the bloop. This ultra-low frequency sounds significantly louder than any known animal swept across the Pacific Ocean for over a minute, its distinctive waveform unlike anything previously catalogued. Initial theories ranged from a colossal, undiscovered marine creature to exotic geological events, creating a profound scientific puzzle. While subsequent research has strongly suggested its origin was likely a massive ice quake, the fracturing of large icebergs in Antarctica, the very fact that it remained undeciphered for so long and the scale of its acoustic energy highlights the immense capacity of the ocean to generate sounds that challenge our immediate understanding. Other acoustic anomalies have presented similar lingering questions. The upsweep. For instance, a long, continuous train of narrow-band upsweeping sounds was detected for years across the Pacific its source initially unknown, and its consistent rising frequency pattern unlike any natural or anthropogenic signature. Another, dubbed Julia, was a powerful short-duration sound of unknown origin, its characteristics hinting at a large dynamic event, yet leaving no clear geological or biological footprint. Then there was Slow Down, a protracted low-frequency sound that gradually decreased in frequency over several minutes, and the whistle, a series of distinct high-frequency tones. Each of these unique acoustic events, recorded by arrays of hydrophones, meticulously placed to listen to the Earth's deep pulse, presented a distinct challenge, a sonic fingerprint that did not match any entry in the vast catalogue of known ocean sounds. Scientists would spend countless hours filtering, analyzing, and comparing these waveforms, searching for patterns, for clues, for any resonance with the familiar. The frustration lay in the fact that these signals, while undeniably real, simply did not fit into the established framework of oceanic acoustics. What makes these acoustic anomalies so compelling is not just their unusual sound, but the context of their detection. They often emanate from regions of profound depth, far from continental shelves, distant from major shipping lanes, and seemingly disconnected from significant seismic or volcanic activity. They are not random bursts of noise. Many exhibit characteristics of sustained energy, sometimes for hours or even days, or they show repetitive patterns, suggesting a consistent underlying process. The sheer volume of water miles deep acts as an immense filter, allowing only the most powerful low-frequency sounds to propagate across vast distances. For a signal to be detected thousands of miles away, it must originate from a source of extraordinary acoustic power, or be generated by a mechanism that is incredibly efficient at channeling sound through the deep ocean's unique acoustic waveguides, such as the SOFAR channel. The very act of discerning these subtle, persistent whispers from the background hum of the ocean requires sophisticated signal processing techniques, meticulously designed algorithms that can extract faint patterns from immense datasets, much like sifting for a single, unique grain of sand on an endless beach. Even more profoundly challenging and far rarer in documented reports are the enigmatic traces of electromagnetic signals purportedly emanating from the abyssal depths. As we explored previously, the deep saline ocean is a formidable barrier to electromagnetic radiation. Its high concentration of free ions acts like a vast conductive shield, rapidly absorbing and dissipating radio waves over incredibly short distances. Conventional radio signals like those used for terrestrial communication simply cannot penetrate more than a few centimeters into seawater before their energy is entirely consumed. Even the specialized extremely low frequency ELF or very low frequency VLF waves used for limited submarine communication can only reach modest depths, requiring colossal transmitters and offering excruciatingly slow data rates. The physics of electromagnetic propagation in a highly conductive medium like seawater is well established, and it dictates that long-range electromagnetic communication from the deep ocean floor should be quite simply impossible. Therefore, any credible report of an electromagnetic signal originating from extreme depths, particularly if it exhibits characteristics of sustained transmission or discernible patterns, would represent a profound challenge to our understanding of fundamental physics. Scientists approaching such a discovery would first rigorously scrutinize the data for any possibility of instrumental error, electrical interference, or misinterpretation. Could it be an artifact of the detection equipment itself? Perhaps a subtle resonance within the deep sea observatory's own electrical systems, mistakenly interpreted as an external signal? Could it be a highly localized transient phenomenon, a minute burst of energy from an unknown chemical reaction that is somehow amplified or channeled in an unforeseen way? These are the initial questions, the methodical steps taken to rule out the conventional before even contemplating the extraordinary. The challenge lies in the sheer improbability. If such signals were truly electromagnetic, originating from miles beneath the surface, they would imply either an unknown natural phenomenon capable of generating and propagating EM energy in a way we do not understand, or a technological source of immense power and sophistication operating under conditions that defy our current engineering capabilities. Could there be a geological process deep within the Earth's crust that generates powerful low-frequency electromagnetic pulses that somehow manage to pierce through miles of conductive rock and water? Some theories, still highly speculative, propose exotic interactions between deep-sea seismic activity, mineral deposits, and the flow of seawater, creating localized electromagnetic effects. However, for these to be detectable at a distance and to exhibit any form of consistent pattern would require a mechanism far beyond our current models. The very scarcity of documented, well-corroborated electromagnetic anomalies from the deep ocean underscores their profound significance. They are the ultimate whispers from the sunken world, hints of phenomena so utterly alien to our surface-bound physics that they compel us to reconsider the very boundaries of scientific possibility. The undecipherable hum, whether acoustic or the far more elusive electromagnetic, serves as a constant reminder of the vast, unexplored territories within our own planet. It beckons us with a quiet, persistent insistence to listen more closely, to refine our instruments and to expand our minds, to encompass the possibility of wonders and mechanisms that lie literally beyond the reach of our current understanding, waiting patiently within the crushing cold embrace of the deep. The instruments and methods of deep-sea detection. To truly listen to the deep, to discern the subtle, undecipherable hum from the known voices of the ocean floor, requires not only immense patience but also a remarkable array of specialized instruments meticulously engineered to withstand conditions that are profoundly hostile to human technology. This is the art and science of deep-sea detection, a patient act of extending our senses into a realm of crushing pressure, pervasive cold and absolute darkness, transforming the invisible vibrations and energetic pulses into decipherable data. At the heart of this endeavor are the hydrophones, the ocean's ears. These are essentially underwater microphones designed to convert the subtle pressure fluctuations of sound waves in water into electrical signals that can be recorded and analyzed. Unlike microphones used in air which detect minute air pressure changes, hydrophones must operate efficiently within an incompressible, dense fluid. Their core often relies on the piezoelectric effect, a fascinating property of certain crystalline materials. When these materials are subjected to mechanical stress, such as the pressure wave of a sound traveling through water, they generate a tiny electrical charge. Conversely, applying an electrical charge causes them to deform, a principle used in active sonar to transmit sound. Imagine a delicate membrane encased within a robust, pressure-resistant housing, patiently awaiting the faintest tremor of water molecules. This subtle squeeze, this imperceptible push and pull of the ocean's breath, is then transformed within the hydrophone's heart into a minute flicker of electricity, a whisper made tangible, ready for our understanding. The design of a deep-sea hydrophone is a triumph of engineering. It must withstand the immense hydrostatic pressure which can exceed 1,000 atmospheres in the deepest trenches, requiring housings made of robust ceramics or specialized alloys. It must resist the relentless corrosive properties of salt water, which can swiftly degrade conventional materials necessitating careful selection of protective coatings and non-reactive components. Furthermore, the constant presence of marine organisms means battling biofouling, the accumulation of microscopic life that can interfere with sensor performance. These sensitive instruments are often deployed individually anchored to the seafloor or suspended from moorings, listening in isolation. Yet their true power often lies in arrays, vast interconnected networks of multiple hydrophones spread across hundreds or even thousands of kilometers of the ocean floor. By precisely timing the arrival of a sound wave at different hydrophones within such an array, scientists can triangulate the source, pinpointing its origin with remarkable accuracy, much like how our two ears allow us to locate a sound in space. These arrays also allow for a technique called beamforming, where the signals from multiple hydrophones are combined in a way that enhances sounds coming from a particular direction, while suppressing noise from other directions, effectively giving the array a directional ear to focus on faint, distant whispers. Beyond the purely acoustic seismometers are crucial companions in this quest. While hydrophones listen to sound waves in the water column, seismometers detect ground motion, the vibrations that travel through the solid earth. Deployed directly on the seafloor, often encased in heavy pressure-resistant spheres or cylinders, these instruments are designed to be exquisitely sensitive to the subtle tremors of earthquakes, the slow creep of tectonic plates, or even the localized vibrations from volcanic activity. By combining data from both hydrophones and seismometers, scientists can distinguish between sounds originating in the water and those generated within the Earth's crust, providing a more complete picture of the deep ocean's dynamic environment. For instance, a deep rumbling sound detected by a hydrophone might be identified as an underwater earthquake if a corresponding seismic event is registered by a nearby seismometer, allowing researchers to accurately attribute the source of the acoustic energy. To search for the truly enigmatic electromagnetic signals, a different suite of instruments is required: magnetometers and electric field sensors. Magnetometers measure the strength and direction of magnetic fields, while electric field sensors detect the presence of electrical currents. These instruments are designed to be incredibly sensitive, capable of discerning minute fluctuations in the Earth's natural geomagnetic field, or the subtle electrical currents generated by geological or biological activity. However, deploying them in the conductive saline environment of the deep ocean presents immense challenges. The high conductivity of seawater rapidly attenuates electromagnetic waves, making any distant signal incredibly faint. Furthermore, the constant motion of water and the presence of dissolved ions can create their own electrical noise, making it difficult to isolate a true signal. These sensors must be meticulously shielded from internal interference from their own power sources and data cables, and their readings require sophisticated processing to filter out the overwhelming background noise. If an electromagnetic signal were indeed detected from the deep, these instruments would be the first to hint at its presence, providing a tantalizing glimpse into a phenomenon that currently defies our understanding of physics. The deployment of these sophisticated instruments is a monumental undertaking, often involving specialized research vessels equipped with powerful cranes and remotely operated vehicles, or ROVs. A common method involves deploying moorings, long lines anchored to the seafloor with instruments suspended at various depths, gathering data over months or even years. However, for truly continuous real-time monitoring, deep-sea observatories represent the pinnacle of deep ocean listening. These are permanent fixed infrastructures, vast underwater networks connected to shore by fiber optic cables that carry both power and data. Projects like the Neptune Ocean Observatory in the Pacific and the Ocean Observatories Initiative, or OOI, off the coasts of the United States are colossal endeavors. They consist of main junction boxes on the seafloor, powered by high-voltage cables from land, which then distribute power and data to numerous instrument packages spread across hundreds of square kilometers. These observatories host a diverse array of sensors, hydrophones constantly listening, seismometers, patiently feeling the Earth's pulse magnetometers, discerning subtle shifts, along with temperature probes, pressure sensors, chemical analyzers, and cameras. They are like vast, silent cities of sensors, constantly awake, relentlessly gathering an unbroken stream of data from the abyss, offering an unprecedented window into the dynamic processes of the deep ocean over long timescales. Autonomous underwater vehicles, or AUVs, and remotely operated vehicles, or ROVs, play complementary roles in this deep-sea exploration. AUVs are untethered pre-programmed robots that can traverse vast areas of the seafloor, carrying their own hydrophones, cameras, and other sensors. They are invaluable for wide-area surveys, mapping and deploying smaller instruments with precision. ROVs, on the other hand, are tethered to a surface vessel controlled in real time by operators and are equipped with manipulators, powerful lights, high-definition cameras, and an array of sensors. They are essential for intricate tasks like the precise placement of observatory components, maintenance sample collection, and close-up visual inspection of anomalous sites, providing the eyes and hands in a world where human divers cannot venture. Once the data is collected, often in staggering volumes, the next monumental task begins processing and analysis. The raw acoustic and electromagnetic signals are often buried beneath layers of noise. The distant hum of ships, the subtle crackle of biological activity, the inevitable electronic interference. Scientists employ sophisticated signal processing algorithms to filter out this noise, to enhance the faint signals, and to search for patterns. Spectral analysis breaks down complex sounds into their constituent frequencies, revealing unique fingerprints of different sources. Pattern recognition algorithms are trained to identify specific signatures, distinguishing between known geological events, biological calls, and potentially unknown phenomena. Source localization techniques, utilizing the time differences in signal arrival at multiple sensors, allow researchers to pinpoint the geographical origin of a detected sound or electromagnetic pulse, guiding further investigation. This meticulous, painstaking work, often involving years of dedicated effort, is a continuous dialogue between advanced technology and human intellect, a patient search for meaning within a cascade of raw data. The quest to listen in the dark is an ongoing, iterative process. A faint, unusual signal is detected. Hypotheses are formed. More instruments are deployed, perhaps in a targeted array closer to the suspected source. More data is gathered, refined, and analyzed. Slowly, painstakingly, the veil of the unknown is peeled back, revealing either a new facet of our planet's known processes, or perhaps something truly unprecedented. This enduring dedication to listening to, patiently extending our senses into the most remote and challenging environment on Earth, is what drives our understanding of the ocean's profound mysteries, compelling us to continue our silent vigil in the deep, ever alert for the next whisper from the sunken world. Geophonic rhythms and hydrothermal whispers. Natural explanations for anomalous signals. Within the deep, encompassing silence of the abyssal plain, where the unknown whispers from the void, scientists meticulously sift through the torrent of recorded data, searching for patterns, for echoes of the familiar, for any hint that a seemingly anomalous signal might in fact originate from a known, albeit powerful or unusual, natural process. before contemplating truly extraordinary explanations. The rigorous scientific method compels us to first exhaust all possibilities within the realm of the understood to listen for the geophonic rhythms and hydrothermal whispers that might mimic the undecipherable yet ultimately stem from the restless heart of our own planet. One such powerful yet often subtle source of deep-sea acoustics comes from the nuanced movements of Earth's tectonic plates beyond the sudden violent jolt of a typical earthquake. These are the slow slip events, or SSEs, a fascinating and relatively recently discovered phenomenon. Unlike conventional earthquakes, where stored energy is released in a rapid, brittle fracture, generating sharp, high-frequency seismic waves, slow slip events involve a gradual, ductile movement of tectonic plates over days, weeks, or even months. Imagine two colossal continental-sized blocks of rock pressing against each other with unimaginable force, then slowly, almost imperceptibly grinding past one another. Not with a sudden snap, but with a prolonged, agonizing groan. While these events typically occur deeper within subduction zones, away from the immediate surface, their prolonged, sustained motion can still generate very low-frequency seismic waves that propagate into the water column. These might manifest as a deep infrasonic hum, a sustained, almost imperceptible tremor that could be mistaken for an unknown source if not carefully analyzed and correlated with precise seismic measurements. The very slowness of these events makes their acoustic signature distinct, a drawn-out, resonant thrum that speaks of immense forces at work, yet without the dramatic, sharp crackle of a conventional quake. Scientists believe that the presence of fluids, perhaps superheated water, within the fault zones acts as a lubricant, allowing for this slow, continuous release of stress rather than an abrupt rupture. Another intriguing seismic phenomenon that produces persistent low-level acoustic energy is deep tremor, sometimes called non-volcanic tremor. These are continuous low-amplitude seismic vibrations that are distinct from both ordinary earthquakes and volcanic tremors. They are often observed in areas where tectonic plates are sliding past each other, particularly in subduction zones, and are thought to be related to the slow movement of fluids water, or magma, within the deep crustal fault systems. Imagine a constant, faint vibration, a subtle, deep pulse emanating from miles beneath the seafloor. Not a discrete event, but a continuous, almost living tremor, like a colossal, unseen engine perpetually running. These tremors are often too weak to be felt on the surface, but can be detected by sensitive seismometers and hydrophones, contributing to the persistent background acoustic energy of the deep ocean. Their rhythmic yet irregular nature could easily be misinterpreted as an anomalous signal if its geological origin is not fully understood, a persistent whisper from the planet's grinding gears. Perhaps one of the most compelling examples of a resolved anomalous signal being attributed to a natural, albeit dramatic geological process is the bloop. This ultra-low frequency, high-amplitude sound, recorded by NOAA hydrophones across the equatorial Pacific in 1997, was truly perplexing. It was significantly louder than any known biological sound, lasted for over a minute, and had a distinctive sweeping waveform. For years, its origin remained a profound mystery, sparking wild speculation. However, subsequent research combining acoustic data with seismic and glaciological observations strongly suggested that the bloop was in fact an icequake. Imagine a colossal iceberg, perhaps miles across, calving or fracturing deep within the frigid waters of Antarctica. The immense stresses within these monolithic ice formations, driven by ocean currents, temperature changes and gravitational forces, can cause them to crack and split with truly staggering force. The energy released by such an event, particularly the fracturing of a large tabular iceberg, can generate ultra-low frequency acoustic waves, powerful enough to travel thousands of miles through the ocean's acoustic channels, creating a sound signature that eerily matched the bloop. The sheer scale of these glacial events, often occurring in remote, unmonitored regions, means that their acoustic signatures, while natural, can be profoundly unfamiliar and powerful, easily mimicking an alien whisper from the distant frozen world. Beyond the purely seismic, the dynamic processes of underwater volcanism and magma movement also generate a rich variety of acoustic and potentially even subtle electromagnetic signals. Deep beneath the ocean floor, molten rock or magma is in constant slow motion, rising through conduits and chambers. This viscous flow can generate deep, resonant groans and harmonic tremors, a continuous rhythmic vibration that suggests the movement of fluids within a confined space. Imagine a colossal subterranean heart, beating with a slow, powerful pulse, its internal movements echoing through the solid rock and into the water column. When magma interacts with seawater in what are known as phreatic or hydrovolcanic eruptions, the results can be explosively dramatic. The sudden vaporization of seawater as it encounters superheated magma creates immense pressure, leading to powerful, localized explosions that would produce sharp, broadband acoustic energy unlike typical seismic events. These eruptions can also trigger rapid chemical changes and fluid dynamics that in highly localized circumstances could theoretically generate transient electrical potentials, though their propagation through conductive seawater for any distance remains a significant physical hurdle. A particularly fascinating source of deep-sea acoustic activity comes from the destabilization of methane clathrates, also known as methane hydrates or methane ice. These vast, icy cages of water molecules trap methane gas within their crystalline structure, forming stable deposits under the high pressure and low temperatures of the deep ocean floor. Scientists estimate that the amount of carbon stored in methane hydrates globally far exceeds all other fossil fuel reserves combined. However, these deposits are highly sensitive to changes in pressure or temperature. A slight warming of bottom waters, perhaps due to climate shifts or localized geothermal activity, or a decrease in pressure due to submarine landslides, can cause these hydrates to rapidly destabilize. When this happens, the solid methane ice instantly dissociates, releasing vast quantities of methane gas in a sudden, explosive manner. Imagine a colossal underwater effervescence, a massive sustained bubbling event, as millions of cubic meters of gas burst forth from the seafloor. This rapid, large-scale release of gas would generate incredibly powerful and distinct acoustic signatures, characterized by a continuous turbulent roar, a deep, resonant gurgle, and a chorus of smaller popping sounds as individual gas bubbles form and rise. These events can last for hours or even days, dramatically altering the local acoustic environment and creating signals that are profoundly distinct from other known geological or biological sources. The dynamics of rising gas bubbles, particularly if charged, could also theoretically generate localized, transient electromagnetic fields, though again, the challenge of long-range propagation in seawater remains. Beyond these directly geological sources, large-scale oceanographic phenomena can also contribute to the deep ocean's natural acoustic background, generating persistent low-frequency sounds that might be mistaken for anomalous signals. Powerful deep ocean currents, for instance, interacting with prominent seafloor topography such as seamounts, abyssal hills, or submarine ridges, can create vortex-shedding phenomena, much like wind whistling around a flagpole, but on a colossal scale. The flow of dense, powerful currents past these underwater obstacles can generate persistent, low-frequency acoustic energy, a deep, resonant hum or a sustained, turbulent roar that is directly linked to the speed and interaction of the current with the seafloor features. These sounds are often continuous and can extend over vast areas, their intensity fluctuating with the strength of the currents, creating a dynamic background that requires careful analysis to differentiate from other potential sources. Even the slow-motion immense forces of turbidity currents, which we touched upon earlier, deserve further consideration as a source of powerful, natural acoustic events. These are not merely landslides, they are dense, fast-moving flows of sediment-laden water that can rush down continental slopes and into the abyssal plains at speeds of tens of kilometers per hour. The sheer volume and velocity of these flows, displacing immense quantities of ambient seawater, generate a colossal, prolonged roar. A deep, grinding sound akin to a massive underwater avalanche. This acoustic signature is broadband and intense, capable of traveling for hundreds of miles, and its duration can be extensive, reflecting the slow, relentless progression of the sediment flow across the seafloor. While often triggered by earthquakes or slope instability, the acoustic event itself is a primary oceanographic phenomenon, a powerful natural voice of the deep. In the patient quest to decipher the ocean's whispers, the meticulous study of these geophonic rhythms and hydrothermal emanations is paramount. By understanding the full spectrum of sounds that our dynamic planet naturally produces, from the slow, agonizing groans of tectonic plates to the effervescent hiss of chemical reactions and the thunderous roar of sediment flows, scientists gradually build a comprehensive acoustic library. Each anomalous signal is then rigorously compared against this ever-growing catalogue of known natural phenomena. Only when every conceivable geological, seismic, volcanic, or oceanographic explanation has been carefully considered, modeled, and, if possible, ruled out, do the truly undecipherable hums retain their profound mystery, compelling us to look beyond the familiar and consider possibilities that stretch the very fabric of our scientific understanding. The deep ocean continues to reveal new, powerful voices, reminding us that even within the known, there are still countless nuances and complexities waiting to be understood, each one a subtle whisper in the vast, dark expanse. Bioluminescent codes and unseen life, the hypothesis of exotic biology. Having patiently explored the deep, resonant groans of Earth's restless geological heart and the effervescent whispers of its hydrothermal breath, our journey now gently pivots towards an even more profound and perhaps more poetic realm of explanation for the ocean's enigmatic signals, the realm of life itself. Within the crushing cold and eternally dark abyss where conventional light cannot penetrate, life has not merely endured, it has blossomed into an astonishing array of forms, developing senses and communication methods utterly alien to our surface-dwelling perspectives. Here in this vast liquid night, the most prevalent form of visible communication is not sunlight, but the living glow of bioluminescence. Imagine, if you will, being suspended in a world of absolute profound blackness, a darkness so complete that it absorbs every photon, every flicker of conventional light. In this perpetually sunless domain, the only illumination comes from within, from the creatures themselves. Bioluminescence is the biological production of light, a cold light generated through a complex chemical reaction within an organism's body. At its heart lies a molecule called luciferin, which, when oxidized in the presence of an enzyme called luciferase, along with oxygen and often adenosine triphosphate, or ATP, releases energy in the form of light with almost no heat. It is a marvel of biochemical efficiency, a natural light show powered by life itself. This living light, manifests in an astonishing spectrum of colors, though blues and greens are most common, as these wavelengths penetrate deepest through seawater, becoming the most effective for communication and vision in the deep. The purpose of this ethereal glow is as varied as the creatures that produce it. For some, it is a lure, a deceptive beacon, drawing unsuspecting prey towards a hidden mouth, like the famous anglerfish with its glowing dorsal fin filament dangling enticingly in the void. For others, it is a defensive mechanism, a sudden blinding flash designed to startle a predator, allowing the prey a precious moment to escape into the encompassing darkness. Some species, like certain squid and jellyfish, can expel clouds of glowing fluid, creating a luminous smokescreen to confuse attackers. Yet for many, particularly in the mid-water column, bioluminescence is a crucial tool for camouflage, a subtle counter-illumination that matches the faint downwelling light from the surface, effectively rendering them invisible to predators looking up from below. Imagine a delicate, shimmering veil of light that perfectly blends with the almost non-existent ambient glow, allowing a creature to disappear into the very fabric of the deep. But perhaps most profoundly, bioluminescence serves as a sophisticated form of communication, a visual language spoken in flashes and patterns across the inky blackness. Deep-sea copepods, tiny crustaceans, can emit specific flash patterns to attract mates. Certain species of deep-sea squid possess complex photophores, light-producing organs arranged in intricate patterns on their bodies, which they can rhythmically activate to signal to conspecifics, conveying information about species, identity, reproductive readiness, or territorial claims. Picture a vast underwater ballroom where countless unseen dancers communicate through elaborate silent light, shows each flicker, each pulse, each sustained glow, carrying a specific meaning within their unseen society. These are not random bursts of light. They are often highly organized rhythmic sequences possessing all the hallmarks of a deliberate, encoded message, a silent, luminous code unfolding in the profound depths. However, even with its widespread use, bioluminescence, being a form of light, faces the fundamental physical limitation of rapid attenuation in seawater. While blue and green light penetrate deepest, even they are absorbed within a few hundred meters, meaning that a bioluminescent flash is a relatively localized signal. It fades quickly, unable to travel across vast ocean basins like low-frequency sound. This presents a challenge if we are to consider bioluminescence as a direct source for the long-range, undecipherable signals detected by our hydrophones. This leads us into the realm of hypothesis, where scientists begin to stretch the boundaries of current understanding, asking how such visual phenomena might translate into the acoustic or even electromagnetic signals that puzzle us. Could it be that vast synchronized aggregations of bioluminescent organisms, perhaps billions of tiny creatures flashing in unison, generate enough energy to create a subtle, detectable pressure wave? Imagine a massive swarm of deep-sea krill, each no bigger than a grain of rice, but numbering in the trillions, simultaneously emitting a burst of light. The rapid chemical reactions involved, or the minute physiological movements required to trigger the light, if coordinated on an immense scale, might theoretically create a collective low-frequency acoustic pulse, a faint hum born from a colossal living light show. This is highly speculative, as the energy conversion from light production to acoustic pressure would be incredibly inefficient. But in the boundless unknowns of the deep, even unlikely possibilities are considered. Another compelling biological hypothesis centers not on light, but on the acoustic emissions of undiscovered or highly evolved deep-sea life. We know that the great whales use low-frequency sound to communicate over vast distances. What if there are other, perhaps even larger or more specialized deep-sea creatures that have evolved similar or even more complex acoustic capabilities. The ocean is still largely unexplored, with scientists estimating that over 80% of its species remain undiscovered. The deeper we go, the stranger the life forms become, often possessing unique adaptations to their extreme environment. Could some of the undecipherable hums, the bloop, the upsweep, or the Julia, be the cause of truly colossal marine organisms? Perhaps creatures so vast or so rare that they have yet to be formally identified. Imagine a creature so immense that its muscle contractions, its movements through the dense water, or its specialized vocalizations generate ultra-low frequency sounds of astounding power, capable of propagating across entire ocean basins, the deep, resonant roar from a living leviathan, a biological voice so profound that it mimics a geological event. These calls might be territorial warnings, mating rituals, or even forms of echolocation, mapping their dark world with sound. The very fact that these anomalous acoustic signals often exhibit complex patterns and durations, unlike the more chaotic nature of many geological events, lends a subtle weight to the hypothesis of a biological origin, suggesting a living source with intent. Even more speculatively, the possibility of biologically generated electromagnetic signals from the deep ocean floor, while profoundly challenging to reconcile with known physics, remains a tantalizing, albeit distant, hypothesis for some scientists. We know that some marine creatures, particularly sharks and rays, possess specialized electroreceptors, allowing them to detect the faint electric fields generated by the muscle contractions of their prey. This demonstrates that life can indeed interact with and generate electrical fields in conductive seawater, albeit typically over very short distances. Could there exist deep within the abyss organisms that have evolved to generate and perhaps even manipulate electromagnetic fields in ways we do not yet comprehend? Perhaps for highly localized communication or sensing. Imagine a creature with specialized organs capable of producing low-frequency electromagnetic pulses, perhaps as a defense mechanism, or even as a unique form of very short-range signaling. The challenge, of course, is the immense attenuation of electromagnetic waves in seawater. For such a signal to be detected at a distance, it would require a source of unimaginable power or an entirely unknown mechanism of propagation that somehow bypasses the fundamental conductive properties of the ocean. This pushes the boundaries of biological and physical understanding, suggesting a form of life that could literally bend the rules of physics as we understand them. But in the vastness of the unknown, such profound possibilities are sometimes whispered among those who dare to dream of truly alien biology. The deep ocean remains a frontier of astonishing biodiversity and biological ingenuity. Life here is not confined to the familiar. It has evolved in countless unique directions, adapting to pressures, temperatures, and darkness that would be instantly lethal to surface life. The discovery of vibrant chemosynthetic ecosystems around hydrothermal vents entirely independent of sunlight shattered previous assumptions about the limits of life. This continuous unveiling of new, bizarre, and resilient life forms compels us to remain open to the possibility that some of the undecipherable signals, the mysterious hums and whispers, could be the voices of organisms we have yet to encounter. They might be communicating in ways we haven't learned to interpret, using forms of energy or patterns that fall outside our current acoustic or electromagnetic lexicons. The very complexity and persistence of some of these anomalous signals suggest an underlying order, a deliberate pattern that could be indicative of a living intelligence, a biological rhythm emanating from the unseen depths. As we continue to listen to deploy ever more sensitive instruments into the abyssal silence, we must always hold in mind the boundless ingenuity of life. The deep ocean is a colossal living laboratory, a place where evolution has had billions of years to experiment far from the familiar constraints of the sunlit world. The hypothesis of exotic biology, of unseen life communicating through unknown codes, adds a profound layer of wonder and possibility to the mystery of the undecipherable hum. It reminds us that our planet still holds vast, uncharted biological frontiers, and that the whispers from the sunken world might just be the distant, ancient calls of life forms, waiting patiently for us to finally learn their language, inviting us to contemplate the extraordinary biological richness that still lies hidden within the deep. The challenges and dangers of deep-sea exploration. To venture into the profound depths of the ocean, to seek out its mysteries and listen to its enigmatic whispers, is to confront an environment that is utterly inimical to human existence. A realm where every breath, every movement, every flicker of light is a hard-won triumph against overwhelming natural forces. Navigating the abyss is not merely a journey, it is a relentless struggle against the fundamental laws of physics, a testament to human ingenuity, and a constant dance with peril. The most immediate and pervasive adversary in this sunken world is the hydrostatic pressure, an invisible, omnipresent hand that seeks to crush every intrusion. As we descend, the weight of the water above us accumulates with terrifying speed, increasing by 1 atmosphere for every 10 meters. At 4,000 meters, the pressure is equivalent to 400 large elephants standing on a single postage stamp. At the bottom of the Mariana Trench, nearly 11,000 meters down, this force escalates to over 1,100 atmospheres. Imagine a colossal, invisible fist clenching tighter and tighter around any object that dares to intrude. For a submersible, this translates into an immense, unyielding squeeze on its hull, testing the very molecular bonds of its construction materials. To withstand such forces, deep-sea vehicles known as submersibles or human-occupied vehicles must be meticulously engineered, often with spherical pressure hulls, made from incredibly strong yet precisely machined materials, like titanium alloys or specialized high-strength steel. These spheres are designed to distribute the immense external force evenly across their surface, minimizing stress concentrations. Even the smallest imperfection, a hairline crack or a minute flaw in a weld, could spell catastrophic instantaneous implosion, collapsing the vessel into a fraction of its size in less than a blink of an eye. The very act of designing and constructing these deep-diving craft is a painstaking exercise in precision engineering, a constant battle against the relentless, crushing embrace of the deep. Hand in hand with the pressure comes the absolute profound darkness. Beyond 1,000 meters, the sun's light is utterly extinguished, plunging the abyss into eternal night. This is not merely the absence of light. It is a sensory deprivation so complete that it can disorient and overwhelm. Explorers inside submersibles rely entirely on powerful artificial lights to pierce this inky blackness. These lights, typically high-intensity discharge lamps or arrays of LEDs, must be housed in pressure-resistant casings, their delicate filaments and electronics protected from the crushing force. Even with these powerful illuminators, the beam penetrates only a short distance, perhaps a few tens of meters, creating a small, intensely lit bubble of visibility within an infinite, consuming void. Outside this fragile halo, the darkness presses in a constant, tangible presence, amplifying the sense of isolation and the vastness of the unknown. The world beyond the light beam is a mystery, a silent, unseen realm where unknown forms might lurk, only hinted at by the faint, shimmering flashes of bioluminescence in the far distance, like scattered stars in a lightless cosmos. Then there is the pervasive, bone-deep cold. As we descend past the thermocline, the temperature plummets, settling at a frigid 0 to 4 degrees Celsius in the abyssal zone. This is not a transient chill, but an eternal, unyielding embrace that permeates every component of deep-sea equipment. Submersibles must be heavily insulated to protect their sensitive electronics and human occupants from hypothermia. Hydraulic systems, robotic arms, and scientific instruments must be designed to function reliably at near-freezing temperatures, where lubricants can thicken metals, can become brittle, and electronic components can malfunction. Batteries, the lifeblood of untethered vehicles, lose efficiency in the cold, shortening mission durations. The relentless cold also impacts the human element, requiring advanced life support systems to maintain comfortable internal temperatures even as the exterior of the submersible sheds heat into the frigid ocean. Adding to these physical challenges is the profound isolation and remoteness of the deep ocean. Deep-sea exploration takes place thousands of miles from land, often in the most remote regions of the planet. Any accident, any emergency instantly becomes a crisis of immense proportions. Rescue operations are incredibly complex, fraught with immense logistical hurdles, and often severely time-limited due to the finite life support capabilities of submersibles. There are no quick escapes, no easy returns to the surface. Once beneath the waves, the submersible and its occupants are utterly alone, a tiny, fragile bubble of humanity suspended in a vast, alien world, dependent entirely on the integrity of their vessel and the flawless functioning of its systems. Communication in this environment is exceptionally challenging. Conventional radio waves, as we've explored, are almost entirely absorbed by conductive seawater, rendering standard wireless communication impossible. Deep-sea submersibles rely primarily on acoustic communication, using modulated sound waves to transmit data and voice messages to surface support vessels. However, acoustic communication is slow, often limited in bandwidth, and susceptible to interference from natural ocean noise such as marine life, geological activity, or even the ship's own propellers. The speed of sound varies with temperature, pressure, and salinity, creating complex propagation paths that can distort or scatter signals. Furthermore, the immense distances involved mean significant time delays in transmission, turning even a simple question and answer into a slow, deliberate exchange. For high-bandwidth data, such as real-time video, fiber optic cables are often the only solution. But these tethered systems limit maneuverability and introduce their own risks of entanglement or breakage. Navigation in the deep is another formidable hurdle. Global Positioning System, or GPS signals, cannot penetrate water. Submersibles must rely on a combination of sophisticated technologies. Acoustic transponders deployed on the seafloor or suspended from surface vessels emit sound pulses that the submersible detects, allowing it to calculate its position relative to these known points. Inertial navigation systems, or INS, use gyroscopes and accelerometers to track changes in position and orientation from a known starting point, but these systems drift over time and require periodic updates. Doppler velocity logs, or DVLS, use acoustic beams to measure the submersible's speed and direction relative to the seafloor or water column. Combining these systems, often with complex algorithms, allows for precise but still challenging navigation in a featureless, lightless environment where every turn, every ascent, every descent must be meticulously planned and executed. The omnipresent danger of equipment failure is a constant companion. In such extreme conditions, even a minor malfunction can escalate into a life-threatening situation. A delicate sensor failing a hydraulic line, rupturing a battery, short-circuiting, or a thruster seizing up. Any of these can compromise a mission. The immense pressure means that even the smallest leak can rapidly become a torrent, and a catastrophic breach can lead to instantaneous implosion. The cold can cause materials to contract and become brittle, while the corrosive salt water constantly works to degrade components. Every system, every component must be designed with redundant backups and fail-safes. But the sheer complexity of deep-sea technology means that unforeseen failures are always a possibility, requiring constant vigilance and rapid decisive action from the crew. While less common biological hazards also present unique challenges. The deep ocean is home to an astonishing array of creatures, many of which are still unknown to science. While most deep-sea life is docile or too small to pose a threat, the possibility of encountering unusually large or aggressive organisms or species that might damage equipment cannot be entirely discounted. Biofouling. The accumulation of marine organisms on sensors and equipment is a persistent problem degrading performance over time. Geological hazards are also a significant concern. The seafloor is not static. It is a dynamic landscape shaped by tectonic forces. Underwater landslides triggered by earthquakes or unstable slopes can create colossal turbidity currents that can engulf and destroy anything in their path. Active hydrothermal vents, while fascinating, spew superheated corrosive fluids that can damage sensitive equipment and obscure visibility. The sudden eruption of a submarine volcano, while rare, would be an unimaginably violent event, posing an existential threat to any nearby submersible. Navigating these dynamic geological features requires constant monitoring and a deep understanding of seafloor processes. Finally, the human factors within the confined, isolated, and perpetually dark environment of a deep-sea submersible cannot be overlooked. The psychological toll of extreme confinement, the sensory deprivation, the constant awareness of immense danger, and the sheer remoteness can be profound. Crews must be meticulously trained, not just in operating the complex machinery, but also in maintaining composure, teamwork, and resilience under extraordinary stress. The successful execution of a deep-sea mission is as much a testament to human endurance and psychological fortitude as it is to technological prowess. The financial and logistical costs of deep-sea exploration are staggering, reflecting the immense challenges involved. Research vessels, submersibles, ROVs, AUVs, and the armies of scientists and engineers required to operate and maintain them represent investments of hundreds of millions, if not billions of dollars. Each dive is a meticulously planned high-stakes endeavor, pushing the boundaries of technology and human capability. Yet despite these immense challenges and inherent dangers, the allure of the unknown, the profound mysteries whispered from the sunken world, continue to draw brave explorers deeper and deeper into the abyss, compelling us to face these perils in the tireless quest for knowledge to finally decipher the secrets held by Earth's most enigmatic frontier. Historical encounters with mysterious ocean sounds, long before the advent of sensitive hydrophones or the meticulous scientific arrays that now patiently listen in the deep, humankind has been tethered to the ocean's acoustic whispers, interpreting its enigmatic sounds through the lens of wonder, fear, and ancient lore. For millennia, sailors and coastal dwellers experienced the vast, restless sea, not just as a visual spectacle, but as a profound, echoing presence. A colossal entity that hummed, groaned, and roared with voices, both familiar and utterly alien. These were the first historical encounters with mysterious ocean sounds, forming the bedrock of legends and inspiring a primal curiosity about the unseen forces beneath the waves. Imagine a lone wooden vessel adrift on the immense dark expanse of the ancient sea. The only sounds are the creaking of the ship's timbers, the rhythmic slap of waves against the hull, and the wind sighing through the rigging. But sometimes from the profound depths below, a strange low rumble would emanate a deep vibration, felt more than heard, resonating through the very structure of the ship. Or perhaps a mournful, drawn-out groan, a sound unlike any known animal, would slowly rise from the inky blackness, a haunting whisper that seemed to speak of unseen, colossal beings. These inexplicable acoustic phenomena, devoid of any visible source in the vast, featureless ocean, fueled the vivid imaginations of mariners, giving birth to tales of monstrous krakens, leviathans, and gargantuan sea serpents whose mighty roars could shake the very foundations of the ocean. The deep, guttural thrum of a distant underwater earthquake, the rhythmic, powerful pulse of a migrating whale, or the eerie, high-pitched creak of shifting icebergs in polar regions could easily be attributed to the breath or movement of these mythical titans. Their unseen presence made tangible through sound alone. The ocean in its vastness became a canvas for acoustic projections of humanity's deepest fears and wildest dreams, a world populated by sonic phantoms. Even closer to shore, certain natural acoustic phenomena baffled early observers. The phenomenon of singing sands or booming sands, found in select desert and coastal regions, has been recorded for centuries. Under specific conditions, when dry sand moves, it can produce a sustained low-frequency hum, or drone sometimes likened to a distant pipe organ, or a deep, resonant bell. Imagine the bewildered awe of ancient peoples hearing the very ground beneath their feet, emitting such an inexplicable, profound sound, a voice from the earth itself. Similarly, in polar regions, the vast monolithic structures of icebergs could produce a cacophony of sounds as they carved, cracked, and shifted. The sudden, explosive crack of a towering ice wall breaking away, or the prolonged, mournful groan of immense ice sheets grinding against each other, could create acoustic signatures that traveled for miles across the frigid water's sounds that would have been utterly mysterious and awe-inspiring to early explorers, easily woven into tales of ice giants or spirits of the frozen seas. These were the known yet often misunderstood voices that shaped humanity's early acoustic relationship with the mysterious deep. As centuries passed and maritime technology slowly advanced, the ability to perceive and interpret these sounds began its nascent, halting evolution. The advent of early steamships with their noisy engines initially masked many of the ocean's subtle voices. However, the early 20th century, particularly during World War I, marked a pivotal shift with a desperate need to detect submerged enemy submarines. This urgent necessity spurred the development of rudimentary hydrophones and passive acoustic listening devices. These early instruments, often little more than sensitive microphones encased in waterproof housings, were deployed from ships lowered into the water to listen for the telltale thrum of propeller cavitation or the faint mechanical groans of a submarine. The sound quality was often poor, plagued by engine noise from the listening vessel itself, and the distinction between a true target and the myriad natural sounds of the ocean was incredibly challenging. Yet even with these limitations, operators would occasionally report strange, unidentifiable sounds, persistent rhythmic clicks, unusual, sustained hums, or deep resonant pulses that did not match any known vessel or marine animal. These early anecdotal reports, often dismissed as equipment malfunctions or operator error, were the very first scientific whispers of the undecipherable hum, hinting at a deep acoustic landscape far more complex than initially imagined. The true revolution in deep-sea listening arrived with the Cold War, driven by the intense clandestine struggle to track and counter enemy submarines. This era saw the deployment of the Sound Surveillance System, or SOSUS, a vast covert network of hydrophone arrays strategically laid out across the ocean floors of the Atlantic and Pacific. Imagine thousands of sensitive underwater microphones meticulously placed at precise locations, connected by miles of armored cable to shore-based processing stations, forming a colossal, silent ear listening to the entire ocean. While its primary mission was military intelligence, SOSUS inadvertently became one of the most powerful scientific instruments ever conceived for ocean acoustic research. Its continuous wide-area listening capabilities, operating for decades, began to record an unprecedented wealth of data, revealing the true acoustic complexity of the deep ocean. It was through SOSUS that many of the most famous and initially baffling anomalous sounds were first systematically recorded. Beyond the predictable sounds of marine mammals' seismic activity and distant shipping, the hydrophones picked up persistent, unusual acoustic patterns that defied immediate classification. There was the upsweep, a long, continuous train of narrow-band, upsweeping sounds detected for years across the Pacific, its source remaining a mystery for a considerable time. There was Julia, a powerful short-duration sound of unknown origin, its characteristics hinting at a large dynamic event. Other strange low-frequency events, often simply categorized as biological or geological, with a question mark accumulated in the data archives, their origins debated among a small, specialized community of oceanographers and acousticians. These were not the fleeting anecdotal reports of earlier eras. These were scientifically recorded persistent signals demanding explanation. One particularly intriguing class of early SOSUS detections involved what were colloquially known as trains, or whistles. These were often long-duration, quasi-continuous signals, composed of multiple closely spaced frequencies, sometimes rising or falling in pitch, giving them a melodic or rhythmic quality, unlike the more chaotic sounds of geological events or the distinct calls of known whales. Imagine listening to a faint, distant, complex musical phrase repeating over and over, yet originating from miles beneath the waves, in a region where no known source should exist. The very regularity and structure of some of these signals fueled intense speculation about exotic biological sources, perhaps undiscovered colossal animals, communicating in ways we couldn't yet comprehend, or even in the wilder fringes of thought, something technological. The sheer scale of the SOSUS network, listening across thousands of kilometers, meant that these sounds were often detected simultaneously by multiple arrays, allowing for rudimentary triangulation and a clearer understanding of their vast propagation distances, further amplifying the mystery of their unknown origins. The historical accounts of these mysterious ocean sounds, from ancient mariners to Cold War acousticians, underscore a fundamental truth. The deep ocean has always possessed voices that stretch the limits of human understanding. The initial response was often one of awe, fear, or dismissal, but with the advent of technology, these enigmatic whispers transformed into scientific puzzles, compelling researchers to develop new theories, new instruments, and new methods of analysis. The early, often secret encounters with these undecipherable hums laid the crucial groundwork for our current pursuit of the ocean's deepest secrets. They reminded us with a quiet, persistent insistence that even on our own planet, vast realms of the unknown still exist, patiently waiting for us to learn their language. These legends of the deep passed down through generations or quietly catalogued in classified archives serve as a continuous gentle beckoning, drawing us ever deeper into the profound acoustic mysteries of the sunken world, encouraging us to listen more closely to the ancient echoing heart of the ocean. Future technologies and the quest for answers. The ceaseless whispers from the sunken world, those undecipherable hums that rise from the crushing cold embrace of the abyss, serve not as a barrier to understanding, but as a profound, compelling invitation. They push the very boundaries of human ingenuity, driving scientists and engineers to conceive of extraordinary new technologies to refine our senses and to probe the depths with an ever-increasing precision and patience. The quest for answers for the true origin of these enigmatic signals is now accelerating, propelled by breakthroughs in robotics, artificial intelligence, and material science, promising to illuminate the ocean's darkest secrets. One of the most significant advancements lies in the evolution of our listening posts, the hydrophone arrays. While the vast fixed networks like SOSUS provided invaluable data, the future envisions far more dynamic, distributed, and intelligent acoustic observation systems. Imagine not just static ears, but a constellation of thousands of miniature, ultra-sensitive hydrophones, each no larger than a human thumb, autonomously deploying across vast, previously unmonitored ocean basins. These next-generation hydrophones will be designed for extreme power efficiency, capable of listening patiently for years on a single long-life battery, or even harnessing energy from the subtle thermal gradients or currents of the deep. Their data processing will occur at the source, filtering out known noise and intelligently compressing information before transmitting only the most relevant anomalous signals, reducing the colossal bandwidth demands of current systems. This network will be less like a series of isolated ears and more like a vast interconnected neural net, each node contributing to a collective real-time understanding of the ocean's acoustic landscape. A particularly promising frontier in acoustic sensing is distributed acoustic sensing, or DAS, utilizing existing and future fiber optic cables that already crisscross the ocean floor. These cables, primarily designed for telecommunications, can be repurposed as incredibly long, continuous hydrophones. Imagine miles upon miles of hair-thin glass fiber, patiently draped across the abyssal plains, each tiny segment acting as a sensor. By sending laser pulses down these fibers and analyzing the minute backscattered light, scientists can detect subtle vibrations and pressure changes along the entire length of the cable. This transforms a passive data conduit into an active, ultra-sensitive acoustic array capable of detecting seismic tremors, distant whale calls, and even the faint rhythmic pulse of an unknown source with unprecedented spatial resolution. The potential to leverage existing global infrastructure for continuous wide-area deep-sea listening represents a colossal leap forward, turning the very veins of global communication into the nervous system of deep ocean discovery. Complementing these advanced listening systems are the next generations of autonomous underwater vehicles, or AUVs. These untethered robotic explorers are becoming increasingly intelligent, capable of navigating complex seafloor terrain for extended periods without human intervention. Future AUVs will possess vastly improved endurance, perhaps operating for months or even years, powered by advanced battery technologies or even by harvesting energy from deep-sea thermal vents or ocean currents. Imagine a silent, sleek silver torpedo, meticulously programmed, gliding gracefully through the abyssal darkness, its array of sensors constantly scanning, listening, and mapping. The most exciting development is the concept of AUV swarms, coordinated fleets of dozens or even hundreds of these autonomous robots working in concert. Each AUV in the swarm could carry a different suite of sensors, some with hydrophones, others with magnetometers, chemical sniffers, or high-resolution cameras, collectively creating a multimodal three-dimensional picture of the deep-sea environment. These swarms would be able to react dynamically to detected anomalies with AI algorithms, directing individual robots to converge on a mysterious signal source, collecting denser, more varied data in real time, effectively allowing us to send an entire expeditionary force into the abyss without risking human lives. For targeted investigation and precise sampling, next-generation remotely operated vehicles, or ROVs, and deep-sea landers will play crucial roles. Future ROVs will be designed for even greater depths, pushing beyond the current limits of 11,000 meters, utilizing advanced composite materials that are both lighter and stronger than current alloys. Their robotic manipulators will possess unprecedented dexterity, capable of performing delicate geological sampling, deploying microsensors with pinpoint accuracy, or even interacting with deep-sea organisms in a non-invasive manner. Imagine a powerful, agile robotic arm guided by human hands from a surface vessel miles above, meticulously collecting a rock sample from a hydrothermal vent, or carefully placing a new acoustic sensor near a suspected source of an anomalous hum. Deep-sea landers, essentially self-contained scientific platforms, will become even more autonomous, able to remain on the seafloor for years, patiently monitoring specific sites of interest, deploying and retrieving smaller AUVs or sensor packages, and transmitting their data periodically via acoustic modems or through optical fiber connections to observatories. The quest to detect and understand electromagnetic signals from the deep ocean floor remains one of the most profound challenges pushing the very boundaries of physics. Given the extreme attenuation of EM waves in conductive seawater, future efforts will likely focus on detecting highly localized, extremely low-frequency ELF phenomena, or on developing entirely novel approaches. Scientists are exploring advanced sensor designs for magnetometers and electric field sensors, making them exquisitely sensitive to even minute transient fluctuations. Imagine a sensor so delicate it can discern the faint electrical activity of a deep-sea organism, or the subtle electromagnetic pulse generated by a hitherto unknown geological process, such as exotic mineral reactions or fluid flows within the Earth's crust that might generate transient fields. Research into magnetotellurics and controlled source electromagnetic CSEM methods is also advancing. These techniques, primarily used for imaging subsurface geological structures, involve inducing electromagnetic fields and measuring their response. While not directly detecting signals, in the conventional sense, they could potentially reveal deep-seated geological structures or fluid conduits that might be responsible for generating localized weak electromagnetic anomalies, offering an indirect but powerful investigative tool. The challenge remains immense, but the possibility of unlocking a new form of communication or energy transfer in the deep continues to drive these difficult cutting-edge investigations. Perhaps the most transformative technological leap will come from the realm of artificial intelligence and machine learning. The sheer volume of data generated by future deep-sea observatories and AUV swarms will be astronomical, far exceeding human capacity for manual analysis. AI algorithms will be essential for real-time processing, capable of sifting through terabytes of acoustic, chemical, and visual data, identifying subtle patterns, filtering out known noise, and flagging truly anomalous signals with remarkable speed and accuracy. Imagine an AI system trained on decades of ocean soundscapes, instantly recognizing the specific signature of a distant earthquake, filtering out the hum of a passing ship, and then alerting scientists to a novel, persistent rhythmic pulse that has never been recorded before. Machine learning can also be used to develop predictive models for geological events, or to correlate different sensor modalities, for example, linking an unusual acoustic event with a sudden chemical plume or a localized electromagnetic fluctuation to build a more comprehensive understanding of complex deep-sea phenomena. This intelligent analysis will transform raw data into actionable insights, allowing human scientists to focus on interpretation and hypothesis generation. Beyond these tangible technologies, the quest for answers also demands a renewed spirit of international collaboration and open science. The deep ocean knows no political boundaries, and its mysteries are too vast for any single nation to unravel alone. Future endeavors will increasingly rely on shared data platforms, standardized methodologies, and collaborative expeditions, pooling resources and expertise from around the globe. Imagine a global network of deep-sea observatories, all contributing their data to a unified open-source archive, allowing researchers from any corner of the world to access and analyze the ocean's whispers, fostering a collective intelligence in the pursuit of discovery. This spirit of shared inquiry will be crucial for mapping the truly vast and enigmatic soundscape of the deep, ensuring that every whisper, every hum, every faint echo is heard and meticulously considered. The journey into the profound depths, driven by the persistent allure of the undecipherable hum, is a testament to humanity's unyielding curiosity. The future of deep-sea exploration is one of unprecedented technological sophistication of intelligent machines, extending our senses into the most extreme environments on Earth. As we deploy these advanced tools, we move closer to deciphering the ancient, mysterious voices of the sunken world, patiently waiting to understand whether they speak of undiscovered geological processes, of unseen colossal life forms, or of something entirely beyond our current imagination. The quest continues, gently drawing us deeper into the profound, silent embrace of the ocean, ever alert for the next revelation. A lullaby of the unseen. As our gentle journey through the ocean's profound depths draws to a contemplative pause, having traversed realms of crushing pressure and eternal night, having listened to the known rumbles of Earth's restless heart and the faint, distant echoes of human endeavor, we arrive at a deeper understanding, not of definitive answers, but of the immense, enduring mystery that still shrouds the sunken world. We have peered through the lens of advanced technology, straining to decipher the whispers that rise from the abyss. Yet many of these enigmatic signals persist, defying our most rigorous scientific explanations, remaining as compelling and perplexing as ever. We have learned of the ocean's extraordinary capacity to conduct sound, transforming every tremor, every biological utterance into a potential long-distance message guided by the intricate physics of the SOFAR channel. We have catalogued the deep, resonant groans of submarine earthquakes, the effervescent hiss of hydrothermal vents, and the powerful rhythmic songs of the great whales, building a comprehensive library of the ocean's natural voices. Even the sometimes misinterpreted acoustic signatures of colossal icequakes like the famous bloop have yielded to patient scientific inquiry, demonstrating how extraordinary natural phenomena can initially mimic the truly anomalous. Yet despite this ever-growing understanding, there remain the persistent rhythmic pulses, the unique spectral patterns, and the subtle, often low-frequency hums that do not neatly fit into any established category of geological biological or anthropogenic origin. These are the truly undecipherable whispers, the enduring enigma at the heart of our exploration, reminding us that the deep ocean holds secrets far more profound than we have yet imagined. The very existence of these unexplained acoustic signals, sometimes lasting for hours or even days, emanating from regions of profound depth and isolation, compels scientists to continue their patient vigil. Could they be the voices of undiscovered colossal marine organisms? Perhaps creatures so rare, so elusive, or so far removed from our known biological paradigms that their acoustic signatures are utterly alien to our current understanding. Imagine a leviathan, a living entity of immense scale whose very movements through the dense water, or whose specialized vocalizations generate ultra-low frequency sounds of astonishing power and complexity, designed for communication across vast ocean basins, a biological language awaiting our translation. The deep ocean, after all, remains largely unexplored, a colossal biological frontier where new species are discovered with every expedition, often possessing adaptations that push the very boundaries of life as we know it. The possibility of a truly exotic deep-sea biology, one that communicates in patterns and frequencies beyond our current recognition, remains a tantalizing poetic hypothesis, adding a layer of profound wonder to the ocean's enduring mystery. Even more profoundly challenging are the faint, fleeting traces of electromagnetic signals that have on rare occasions been reported from the abyss. The fundamental physics of electromagnetic wave propagation in conductive seawater is clear. Such signals should attenuate almost instantly, unable to travel more than a few meters. Yet if these rare detections are indeed valid and not the product of instrumental error or localized interference, they compel us to consider possibilities that stretch the very fabric of our scientific understanding. Could there be unknown geological processes deep within the Earth's crust? Perhaps exotic interactions between mineral deposits, superheated fluids, and immense pressure that generate transient low-frequency electromagnetic pulses, capable of piercing through miles of rock and water in ways we have yet to comprehend. Or could there be a form of life so utterly alien, so uniquely adapted to its environment, that it has evolved mechanisms to generate and perhaps even manipulate electromagnetic fields on a scale or with an efficiency that defies our current biological and physical models? These are not easy questions, and the answers, if they exist, will undoubtedly reshape our understanding of both life and physics in the most extreme environments on our planet. The quest to decipher these mysteries is an ongoing testament to human curiosity and technological prowess. From the deployment of vast interconnected hydrophone arrays, meticulously listening to the pulse of the planet, to the development of intelligent AUV swarms, silently gliding through the abyssal darkness equipped with an array of multimodal sensors, our ability to probe the depths is continuously expanding. Distributed acoustic sensing transforming existing fiber optic cables into colossal continuous hydrophones promises to unlock an unprecedented wealth of acoustic data from previously unmonitored regions. Artificial intelligence and machine learning algorithms are becoming indispensable tools, sifting through torrents of raw data, identifying subtle patterns and flagging the truly anomalous signals that escape human detection. Each technological leap, each new method of analysis brings us closer to understanding, yet simultaneously reveals the boundless extent of what remains unknown. The deep ocean, in its immense scale and profound complexity, serves as a constant, gentle reminder of the limits of our current knowledge. We have explored less than 5% of its abyssal plains and trenches, leaving vast, uncharted territories ripe for discovery. The pressure, the cold, the darkness, and the sheer remoteness continue to guard its deepest secrets, allowing nature's most extraordinary phenomena, and perhaps its most alien life forms, to flourish, unseen, unheard, and uncatalogued. The undecipherable hums, whether they are the distant echoes of a new geological process, the calls of undiscovered titans, or something entirely beyond our current imagination, are the ocean's enduring lullaby, a soft, persistent whisper from the unseen world. They beckon us to listen more closely, to dream more broadly, and to continue our patient, humble exploration of the last, true wilderness on Earth. The deep ocean continues its slow, rhythmic breathing, its vast, dark expanse holding countless wonders, waiting patiently for our deeper understanding. And so, as we gently drift away from the profound, echoing depths, leaving behind the immense pressures and the eternal night, we carry with us the quiet resonance of the ocean's enduring mystery. Just as the deep holds its undecipherable hums, its subtle, persistent signals emanating from unseen sources, so too does the human mind possess vast, unexplored realms, filled with its own gentle currents and profound, unspoken thoughts that surface only in the tranquil quietude of sleep. Allow your consciousness to soften and expand like the vast, dark waters themselves, as your thoughts begin their slow, graceful descent, settling like fine marine snow upon the quiet, abyssal plain of your inner world. Surrender now to the vastness, to the gentle, rhythmic pull of the unseen, knowing that even in the deepest slumber there are wonders waiting to softly unfold within you, carried by currents of peace. May the ocean's deepest, most peaceful whispers now cradle your dreams, guiding you into a profound and restorative rest until the gentle light of morning calls you back to the surface. Good night.